Confidence intervals were our first steps into inferential statistics. We're going to have some information about a sample, and we're going to use that sample information to make an estimate about where we think the population parameter actually falls. For example, if 47 out of 112 people support a candidate, we're going to find a 90% confidence interval, I'll abbreviate that as CI, for the population. So if this is really a random sample and 47 out of 112 support the candidate, where do we think the entire population is actually going to fall? This is similar to what you see done actually on news media all the time when they try to estimate where the population falls when they talk about that plus or minus margin of error. First, we need to know what our proportion is to start off with, our p hat. That's going to be the 47 out of the 112 that support the candidate. And when I do 47 out of 112 on the calculator, I get 0.4196. The next thing we need to know is our z critical value for the alpha over 2. In this case, z for a 90% confidence interval, where we put 90% in the middle. That's going to leave 10% for the two outsides, and so each tail has 0.05 in it. I'm going to go on to Excel and do a norm.s.inverse of the 0.05 to figure out what is that critical value, that z alpha over 2. I'll say equals norm.s.inverse 0.05. My critical value is 1.645. And we can ignore the negative because it's going to be on both sides. We're going to add and subtract the error. Now we're ready to actually figure out what is the error between my sample of 41% and the entire population at the 90% confidence level. To do that, we'll take our z value of 1.645 times the square root of our p, which is 0.4196, times q, which q is 1 minus the p, or 1 minus 0.4196. So q is actually equal to 0.5804. And then we divide by the sample size, which is 112. These formulas are on the formula sheet for the course. You do not need to memorize these formulas, but you do need to know which formula to grab and which formula to use in which context. When I do this on my calculator, I end up with 0.0767 as my error, which means my original proportion of 41% could be off by as much as 7%. That's what we mean when there's a 7% margin of error. So we can take the 0.4196 and subtract the error of 0.0767. And we can take the 0.4196 and add the error of 0.0767. When I do that, we get a lower limit of 0.3429. And we get an upper limit of 0.4963. This means we can say we are 90% confident the true proportion of people who support this candidate is between 34% and 49%. What's interesting is it's definitely less than 50%. Not good for the candidate. Let's do another confidence interval. Let's do one for a mean. Let's say a sample of 48 people owned an average of 7.2 smartphones in their 20s. The standard deviation of the sample was 1.3. We're going to make a 95% confidence interval, CI for confidence interval, for the number of cell phones, smartphones that people in their 20s have owned. Again, we have our sample size, just recording it here as 48. We've got a sample mean here of 7.2, and we have a sample standard deviation of 1.3. With means, we need to use the t-distribution for alpha over 2. So in this case, we want a 95% confidence interval, which means we want 95% in the middle, which leaves 5% for the outside and 2.5% on each side. So this is going to be equals t dot inverse. We want the 0.025 in that left tail. And then we need to tell it the number of degrees of freedom. Remember, the degrees of freedom is always one less than the sample size. So we're going to do t dot inverse 0.025 with 47. T dot inverse with 0.025, and the degrees of freedom are 47. And we get our critical value of negative 2.011. We can ignore the negative because we're going to add and subtract it to the mean anyways. 2.011 is the critical value. We're ready to now find the error. How far off is our mean of 7.2 from the actual mean? The way we calculate the error with the t is we take the t value of 2.011, multiply by the standard deviation, which is 7.2, and divide by the square root of the sample size, which is 48. Again, these formulas are on the formula sheet, so you don't have to memorize them, but you do need to know how to use them. Putting this in the calculator, I find out my error is approximately 2.09, which means my smartphone value of 7.2, we can subtract the 2.09 error, or we can add the 2.09 error. When we do that, we get a lower limit of 5.11 and an upper limit of 9.29. This means we are 95% confident that the number of smartphones owned by people in their 20s is between 5.11 and 9.29. We did one other confidence interval in this class, specifically with the slope of the regression line. We're going to find a 99% confidence interval for the slope of the regression line. Let's say x is 1, 2, 3, 4, 5, 6. And the y's for each of those values were 41.2, 38.9, 34.78, 33.36, 31.64, and 28.12. I've copied this data onto Excel. We're going to do the rest of this problem on Excel because the formulas are a little involved and Excel makes the calculations easier. First thing I need to do is know what the slope is of that regression line that I'm estimating. To do that, we can go to the Insert tab, select my scatter plot chart. Let's make it a little smaller. And I'm going to add to it a trend line. That is the line of best fit that we're going to estimate. Double-clicking that line, I can select to format that trend line, and we're going to display the equation on the chart because we need to know what is that slope that we are estimating. I'm going to put it over here just so that we have it for safekeeping later. And the slope is negative 2.5314. That's the slope that we are estimating for the population. Before we can use the formulas on our formula sheet, we first need to know the sum of the x squareds, the sum of the y squareds, the sum of the xy's. So to do that, we'll have Excel do the hard work. We'll say equals, click the x and square it, equals, click the y and square it, equals x times y. And then we can take those formulas and we can copy them down. I said we needed the sums of each of those, so we can say equals sum, open a parentheses, and select the column that we're in. And then I'm going to copy that formula across. And now we've got all the sums that we need in order to follow the formulas on our formula sheet. We need to first find SSX, then SSY, then SSXY. For the sum of the squares of the x's, we'll say equals, and our formula sheet says that's the x squared minus the x's squared divided by the sample size, and we see there's 6 values, equals, for the sum of squares in the y direction, we'll take the sum of the y squareds minus the sum of the y's squared divided by the sample size of 6. We've got the SSY. Now we do the SSXY formula, which is equal to the xy's minus the sum of the x's times the sum of the y's divided by the sample size of 6. Now that we know those values, we're ready to find our standard error formula. For the standard error, again, using the formula sheet, we're first going to start off with the square root. We'll need an extra parentheses for the numerator. We'll grab the SSY, subtract the slope, times the SXY, close the parentheses on the numerator, and divide by the sample size minus 2, which is 6 minus 2. Close the parentheses on the square root. That is going to be our standard error. The other piece that we need before we can find the error is we need to figure out what the t sub alpha over 2 is. Remember, we wanted a 99% confidence interval. That's the center of the graph, which means 1% is on the outside and 0.5% is in each tail. So when we do our t alpha over 2, we'll say equals t dot inverse. The probability in that tail is 0.005. That's 0.5% as a decimal. And the degrees of freedom are, with regression, 2 less than the sample size. The sample size was 6, so the degrees of freedom are 4. My t-value is negative 4.60409. When we do this, the t-value is going to be negative. We don't want a negative t-value, so I'm just going to change the formula slightly and put a negative in front of it. So now when I grab it, it's a positive 4.60. Because now we're ready to calculate the actual error. How far off is our slope of negative 2.53 from the actual population slope at the 99% confidence level? For the error, it's going to be the t-value that we just calculated times the standard error divided by the square root of the SSX. Again, these formulas coming right off your formula sheet. You don't have to memorize them, but you do have to know how to use them. We're ready now to find the low and high values for our confidence interval. For the low value, we'll take our slope and subtract the error. And for the high value, we'll take our slope and we'll add the error. And so we can now say that we are 99% confident that the slope of the regression line is between negative 1.71 and negative 3.35. There is lots to practice with these confidence intervals, and we also have one more video left where we're going to review our hypothesis test.